So we're just like implementing this DSL for these two DSLs actually, right? For business rules and validation rules, and we're tackling some of these constraints that we must attain in order to implement exactly what we want, right? Validation rule dependent environment, we've done that. Validation rules are sequentially composable. We use monad for that. Business rules can be combined, and the input to a validation rule or to an effect after an event must match the event's contents. We are using GADTs for that, and dispatching events we're going to see short after that, right? So back to the code here. It's talking about how existential types allow us to hide some types from the result, right, of a function of a data type, for that matter. And we're using this prism thing here, right, this function from an f to maybe a, right? This basically means that from f, I can extract maybe an a, okay? And given that I can extract from any event, any parameterized event, a e, maybe an e, right? And we can pass in that thing to a validation rule. This means we've got a business rule. And for an after rule, right, given that we can match an event with an e, right, that from this event we can extract maybe an e, and we can pass that into this effectful function here, we then have got another business rule here, right? We can implement this as an abstract syntax tree using GADTs, generalized algebraic data types. These give us some power, which we're not using fully here, but they give us existential types, right? That, for that matter, like that we can hide any type that appears here on the left-hand side from the type signature, okay? So a guard rule is basically given that we can match an event with an e, the same thing as above, right? Given that we have this e, produce a validation rule, we've got a business rule, okay? Same thing here. The important thing here is that so that if we're hiding this e here, we don't know exactly what it is, right? So in order to consume a value of this guard thing here, in order to consume this value or this value, we must be able to case on any e, right? E has to be like doubly polymorphic. It has to have another rank of polymorphism, right? So we're not doing that explicitly here, right? But we must be able to do that if we wanted to, okay? So I'm not going to go over the code for dispatching an event. Like, this is our interpreter, right? It interprets a set of rules into maybe an effect, right? And what exactly happens here is that given a set of rules and an environment, we dispatch a specific event and we collect the results of the executed rules, right? Which are the effects here, okay? And nothing means that a validation has failed, and just anything means that no validation has failed, but we could have even like performed no validations at all. Yeah, even though no rules exist in the set for such event, okay? Not going to go over this. You can try implement it yourselves as homework. Like, you have this this reference implementation here. Okay, it's well documented, I guess. Okay, because I've got some other cool stuff that I'd like to show, and just in order to show you that all of this works, I'm going to go to main here, right? So in the main file for this program, we have this set of rules here, right? In order to buy a product, we validate a purchase. In order to buy a product, we also validate the user billing info. And after buying a product, we send a purchase email, right? This all happens in the IO monad. We have this env here, which is defined as just this. We just have a user that could be authenticated at the moment. And we have this authenticate helper here, right? The validate purchase function is the same as I've shown in the slides, okay? We check if the user is authenticated, if we have the available quantity of the ordered product, if a price exists in the product, if a country exists in the user, and then we're done, okay? Validating a user's billing info, we just authenticate them, check whether the billing info exists.
I'm sorry, why do we need this done combinator for? Can we just kind of finish the computation at this point? What's the done for?
The done, no, the done is just syntactic sugar. Yeah, I forgot to show that. 1 second. Yeah, done is just syntactic sugar for return unit, okay? And off is just syntactic sugar for this thing. These are not completely necessary at all. I even think that these are confused and are bad to use because people are used to these patterns in Haskell, right? But it's just to show that you can have syntax sugar also in your language if you want to, okay? So yeah. So just to run these things, just so you can see that it works. If we're dispatching an event to that set of rules, given this environment here, right, where we have this user here who's testy Mac test face, and he's got billing info, he's got country info, so he should pass the validation. And we're dispatching this event of buying a product in this purchase, right? We're buying nothing. We're buying nothing. We've got 1,000 units of nothing. We're buying 55 units of nothing, right? And we're just validating whether that works. If this works, right, after buying a product, we're going to send a purchase email, and hopefully we're going to see that here. Did I? Okay, I'm in the wrong folder. So we see that we are sending an email to the user, so the rules have passed, okay? If I change this perhaps to purchase 2, where purchase 2, we're buying this test product, and we only have 2 units of it, but we want 10 units of it, it's not going to work. I didn't save this, okay. So we're going to see validation failed here, okay? If we change this user to some user that doesn't have the info, this is also going to happen, okay? So, yeah, that's this basic example. Like we have seen here that we can use functions in order to have this sort of global environment. We can use monads to sequentially compose actions. We can use GADTs or existential data types to hide some info from the type so that we can combine different things when we want to. And we can interpret things into the IO monad to have effects, or to any effectful monad to have effects, okay? Does anybody have any questions? Anybody got something from this? Cool. So I have a bunch of exercises here. We're obviously not going to go over them. This is just like homework if anybody wants homework. If you have free time, I don't know. If you're masochistic, I don't know. But what exactly should happen if we wanted to depend on a database to perform some validations, right? This is one exercise you can do, one thing you can think about. What if we wanted to add proper error messages, like when a validation failed, we could add custom error messages to each validation? It just involves changing something there. It's pretty simple. We could try expressing the rules with both deep and shallow embedding. We've done that with deep embedding first. And what if we wanted to have a pipeline instead that is like feeding the validated outputs? Like imagine that now validation rules have outputs. What if we wanted to feed those into the after rules, right? One possible solution requires having only a single type of rule, right? Hopefully that can lead someone to the right way. And more homework, more food for thought. What if we wanted validation to be written in terms of classic monad transformers, right? It's pretty easy, I guess. How could we statically render validations as document text? We do need to have some drastic changes in order to be able to do that. And how can we restrict the type of effects that can be performed after each event? This is hard. We can either use some records of effects or we can use constraint kinds, which is pretty cool. Does anybody have any questions? I'm going to post these slides, by the way, so you can refer to all of this and in the repo later. Does anybody have any questions? Okay, so now for the last part, we're going to see another example, which is chatbots with indexed monads. So we've seen monads, now we're going to see another special type of monads, which can do some pretty cool stuff in the type level. And that means, we don't need that. That means that we can enforce some type of protocol in the type level, right? Given that this is the definition of a chatbot, right? Imagine this is the definition of a correct chatbot, right? This is a state machine. That means like we're just starting in this state, this start state, and we can use this start action here to go to the answer state, where in the answer state we can only answer, right, the user, and we go to the ask state, and from the ask state we can either finalize or ask the user for some information. We get back to the answer state, right, and we can stay in this cycle, right, of asking and answering questions from the user, where we can finally finalize the chatbot. And from the finalized state, we're in a state that accepts something, and we're basically done. We can't do anything anymore, okay? So what exactly can we use to do that? Anybody has any ideas? Like to enforce that any chatbot that's going to be produced attains to these rules, and that like after performing an ask action, we can not ask again before answering the user something.
Phantom types.
Sorry?
Phantom types.
Phantom types, exactly. Yeah, that's a great answer. Yeah, that's a good answer. Before I go into that and define what a phantom type is, I'm going to talk about indexed monads. So hopefully some of you can imagine that if we want to build a sort of useful chatbot, we're going to need monads, because we want to be able to refer to the answers the user gave us in order to ask them something or whatever. Like we want to be able to refer to previous values that were produced as effects in order to continue like interacting with the user. So we have another special type of monads which are called indexed monads. You can do that for basically any type class. That basically means that we encode these protocols in the type level. That basically means that, we encode if we think of these as monadic actions, right? We can then encode the initial and the final state in the types, right? So for example, for the answer action, right, we're probably going to produce nothing because it's just an answer action. We're going to produce unit after this, right? So before answering, we must be in the answer state, and after answering, we are in the ask state, okay? So we can use these things called indexed monads. I'm going to show just this one. So in order to have a monad, we have to have a functor, so we're going to define the whole hierarchy here, right? An indexed functor, f, is something that, just like a functor, takes a function from a to b, and from f of a, we can get to f of b, right? This x is the initial state before performing this action, f, right? And y is the state after performing that action, right? Mapping over a context doesn't change the effect, doesn't change anything about the context, so we're still in the same initial and final states, okay? An applicative, if you all remember from the last session, we have this apply combination. Now we have I apply and I pure, right? So in order to embed a pure value A inside an effectful context, which is this M, right? We arrive in this, we get this MXX of A, right? Where the initial state is the same as the final state, because we cannot assume anything about this context because it is pure, okay? In order to sequence two actions which are not like sequentially dependent on each other, like only the values, the pure values produced by these actions depend sequentially on each other. If we have an MXY, right, it starts in the X state, ends in the Y state. And if we got another one that starts in the Y state and ends in the Z state, we get another bigger one that starts in the X state and ends in the Z state. Can everyone see that? Okay. If anyone has any questions at any moment, please ask. So after that, we just specialize the monad type class. It's the same thing, right? We get iBind, which is basically the same thing as bind if you hide the indexes here, okay? If we get an action that produces an M but starts in the X state, ends in the Y state, and we've got a function that from an A produces another effect that starts in the Y state, ends in the Z, we get one that starts in X and ends in Z. So what we'd like to build is basically this. Ignore this thing here, okay, this ix.do. I'm going to explain that, okay? This is pretty cool, by the way, right? want to build something like this, okay? We start, and this thing is a parser, which we can ignore for now, like we're matching any message that the user sends us here, okay? And after we start and the user interacts with us, and this means, right, that we cannot, this protocol here means that we cannot start bugging the user, right? We only start the chatbot after we have received a message, okay? And after starting, we can answer, hey there. We can ask for preferences. We get a language preference, and we can loop asserting preferences of the user. And if they got the answer right, we can say nice and finalize, okay? Just expanding all of this stuff here, okay? It's basically the same thing, right? I just expanded this ask preferences and assert preferences, okay? We're asking the user, this is the ask action. We've got 4 actions from what we saw, right? Start, ask, answer, and finalize, okay? So we're first asking the user, and we're passing in a parser, right? We're parsing the language, the message from the message that they sent us. This is wrong. This shouldn't be a record, right? It should have been just prefers. I can edit that later. And then we're looping, right? Given that we have this answer, we're looping this function here, okay? If the language is pure script, we break the loop and answer nice and finalize. If the answer is Haskell, although we say, which one do you really prefer? And we ask them again for that, and we continue, okay? And we finally answer nice and finalize. So can anybody here tell me something interesting about this loop block? Like, how does this loop block work? Yeah, I should have specified better, sorry. So it's basically like that. In order to be able to loop something, we must ensure that we arrive in the same state that we have started, right? So here, if we're in the answer state, right, because we have just asked, we must end in the answer state where we can only answer, and that's why we can get this thing here, okay? I'm going to show this, that it really works in practice. Like that we actually get some type errors here. So main. Oops. So it's the same thing here, okay? We start and match on any input from the user. We answer hey there. Ask for preferences, loop, asserting preferences, we answer and finalize, okay? Where these two have these definitions. So let's just run this thing here. So it's now awaiting for my input. So it can start. I didn't save probably. Okay, it's waiting for my input. Oh, why is it not working here? It's probably I need to build it. Yeah, my make file is not working correctly. So it's waiting for my input, and now, oh, what is happening here? I'm probably in the wrong folder, I guess. No. Yeah, this is where live coding goes wrong. Yeah, can do some make clean here. Oh, this is going to take some time. Shit, shouldn't have done that. But anyway, we can go over this anyway. Like, this thing is completely inferable, okay, the type here. But I'm going to go over the definition first before we see that it works, because we need to install a few modules first, okay? So the first thing we can do is like properly define this protocol, right? Since we have seen that in order to have an indexed monad, we track the initial and final states as types. We need types in order to represent all states, right? Different types, for that matter. So since we have 4 different states here, we're going to have 4 different types. Oh, sure, please.
So can you go back to the interface of a visitors?
state in the I apply that you can. It seems a bit weird that you can change the state while you're producing the function that you're going to apply.
It's mostly because like you have to consider these things as individual blocks, right? This is a valid action too, and this is a valid action too.
The right-hand side seems normal, but in the left-hand side you're basically producing a function, right? You're not applying the function.
Yeah, I'm not applying a function, exactly. We can produce a function like if you have an array of functions, that's a functor of functions, right?
So while you're producing the function, you can also make a transition. And that seems a little bit odd to me, that you're allowing that.
It's probably more useful if we see this thing as this here too, right? mxya to myza x. Oops. Yeah, the perks of using Google Slides for your slides. Just gonna make this a comment now. Yeah, these two things are isomorphic. Okay, so we have an action that produces an A. We have that should have been a B, actually, and we have an action that produces a B here. Then we have an action that produces A and B. We can get one, right?
I think the question is about the state change that occurs when we create the function.
Yeah, so exactly. This happens. This, like the transitions, they're dependent on the individual implementation of this type class, right? They depend on the instance. And we're going to see that in this case, we're not using these types for real, right? But we can still make this transition if we only define these the instances validly.
Thank you.
Sure.
Why these states are dependent, actually the actions are independent?
That's from the definition, from the very definition of like sequencing two actions, right? So if we have one action and we want to run another action after it, right? One changes the state in some way, and the other one changes the state in another way, but depends that we are in that current in the end state of the previous one.
Aren't truly independent because the initial state of the sequence of the action needs to depend on the final state or the current state of the first action.
Yeah, exactly.
Okay, so that's just definition of Redux simply.
Yes, exactly. Like they're independent in the sense that this effect here is always going to be the same, independently of what value A has, okay? We cannot change the effect that's going to happen here. We can only change the B, right? Okay, so hopefully it is built now. And it's okay. Yeah, it looks like I'm in the wrong folder here. Just 1 second. Okay. Like, it's saying that it's building the project in the wrong folder. So, yeah, I wonder what's going on here. Anyway, I'm going to go to that other folder and oh, it doesn't even exist. Okay, yeah, I was in the wrong folder, that's true. Okay, so now it will work. Okay, sorry about that. So we're now running this chatbot here, right? Hopefully you can see it okay in action. So which one do you prefer, Haskell or PureScript?
Haskell.
Haskell, okay. The bot doesn't agree with you? So which one do you prefer again?
Still Haskell.
Still Haskell, okay. Yeah, it doesn't agree with you. So I'm going to answer for it. Yeah, he agrees with me. Nice bot. So yeah, this compiles works, okay, but what would happen if we, instead of answering here, we wanted to ask the user something else? What if we wanted to ask, like, why are you leaving now? Why are you leaving now? It's a sad bot, and he's asking why are we leaving, right? We're going to get a compile error here, okay? Okay, yeah, that's because I didn't supply a parser here, but okay. Now we get the correct error. Like, it says it could not match the ask type with type answer, okay? And this means that it expected an answer type here, right? It expected an action that starts in the answer state, but we're giving it an action that starts in the ask state, so that's not valid. And that's how we enforce this protocol here, okay? I'm going to show you now the definition of these types, okay? So in order to define this protocol, we just define the type, them as types, okay? We have the start state, we have the ask state, we have the answer state, and the finalized state, okay? And as Chris said, we're going to use phantom types for that in the actual implementation. But for now, we're treating these abstractly. We have this start action, right? If so, from this diagram here, the start action that jumps from the start state to the answer state, right? So given any parser that takes a string and produces any A, we're able to produce this thing that is a indexed monad chatbot that starts in the answer state and ends in, starts in the start state and ends in the answer state while producing this A value, okay? The ask action, the second one here, oops, I should have inverted these things, right? Okay. The answer action, the second one here, right, starts in the answer state and ends in the ask state. So hopefully we can all see that it takes a string to answer the user and starts in the answer state, ends in the ask state, produces nothing, produces unit. This is pure script, by the way, so unit is this instead of this. And the ask function here, the ask action, it takes a string in order to ask the user for something, takes a parser that produces an A, and start produces an action that starts in the ask state, ends in the answer state. And we can loop between those indefinitely until we're finally back to the ask action, and we can finalize with finalize. Oops. And we can finalize. So finalize is just this empty action that ends the thing because it produces nothing. It doesn't do anything actually in the actual implementation, but it starts in the ask state and ends in the finalized state. And since it ends in the finalized state and we don't have any other function, any other combination here that starts in the finalized state, we can say that IX monad chatbot works basically like this state machine here, okay? From the finalized state, we don't have any action that starts on it, so we can't do anything after that, okay? Not going to go over the whole implementation of how this works, but hopefully we can see something even more interesting than that in a few seconds. First, I need to ask if anybody has any questions at all.
Could you model a state machine where you can go to two different places instead of only to the next one?
Yeah, that's an exercise here. But yeah, we can go over that if you'd like to. Yeah, yeah, exactly. Exercise lab to the reader. But we can go over that here if you'd like to. Yeah, how can we allow, yeah, this is another thing. Yeah, but it's basically the same thing, right? How can we allow multiple consecutive answers and questions while keeping the initial and final state transitions? So it's basically like, what if we...
A bit different question, but maybe in the same space, I would say. So what if I wanted a protocol in which validity of state depends on more than one previous state? I got two states back.
Mm-hmm.
So is the preferred approach? I see two approaches. One is to kind of extend the index monad to keep track of using more phantom types, more than just two, to keep track of that. That would be one approach, I guess. And the other would be to just create combined states. What would be the better way, in your opinion? Or maybe something else?
So this could be characterized as a non-deterministic automaton, right? Yes, in some sense. So if you were to model this as a deterministic automaton, you'd need to have combined states, right? Because that's what you do when transforming.
Like a standard algorithm of creating a deterministic automaton.
Yeah, exactly. So you'd have to have combined states, right? Another possibility is like it's possible in pure script to do this with row types because you can always combine things with that. And I was hoping to show something interesting in pure script, but yeah, that's why the bot says a pure script. Extensible row types, yeah, open rows. Exactly.
I think you could also use this, do that with type families, which result in constraints, for instance. So you could say, okay, well, my index variables are just going to keep track of every previous state that I've been in, and then your next index action wouldn't have a concrete required state that's moving into it, but it would assert a constraint over that index, and you could say that the constraint is, well, this type level list must contain at least these two states or something like that.
Yeah. It's a nice approach. And with that, we can even like model like a limited list, right, that keeps only track of 2 elements instead of all the states that went past. So yeah. Would you like to try and implement this thing here? Okay. The other question I'm going to leave for later. Okay. So how exactly can we allow multiple consecutive answers and questions while keeping the initial and final state transitions? And that means basically how exactly can we add also a loop here and a loop here, right? Such that answer also brings us to this same state and ask also brings us to the same state, okay? There are 2 approaches for this, right? One we have said like is to create other states, but this has the caveat that we won't be able to use the same answer function for that. We have to model a different transition to that, right? The other approach, as Chris suggested, we can use type classes for that, right? We can use a type class that identifies this state as sort of like askable, right? And this state is sort of answerable, or both of them, I guess. I have to remember that. But yeah, we can try and go over that. Okay, I've tried doing this exercise a while ago, so I don't exactly remember how to do it. But we need to have some way of like going back to it. Like we need to have some way of saying this answer foo answer bar. So the thing here is that this has type m answer ask unit, and this also has type m answer ask unit. So we can't sequence them in the way they're currently implemented, okay? Because in order to add a new action here, we would need this to have type ask, and this could be any other thing, okay? So how exactly do we do that? Well, there are 2 possibilities here again. We can make this thing polymorphic, some s, and say that it's like an answerable state, answerable and askable, right? It's something like that you can both ask and answer for. Okay, and here it takes the same thing. Not entirely sure if that's going to work because I don't know how type classes work with like producing values instead of consuming values, but I think it should work. Another answer is like adding a type class such that this thing, yeah, it's basically the same thing, right? Okay. Yeah, I just said the same thing twice. It's basically like saying that we have this state here, okay? But this also this produces the ask state, okay? And we need to implement an instance of ask answer for both ask and answer, okay? So we can try that. Class ask answer state doesn't need to have any methods because we're not using those. So we just say instance ask answer ask and answer. Okay. So now what we're left to do is just change our combinators to use these classes. Okay. So we want to do that first to the answer stage, just so it stays simple at first. So we need an ask answer here. and that's it. I think this is going to work. Let's try.
Name the instance.
Oh yeah, this is pure script. Thanks. So in pure script we need named instances. So yeah. Oops. Answer. Okay. Yeah, we need explicit. Oops. We need explicit for alls here too because this is pure script. And yeah, it works in the definition, right? So I think it's also going to work like in the remaining modules. Oops. Yeah, no. Okay, it fails in the implementation, so all right. It's just because I've added these type annotations here, but it works now if I remove them. Just going to remove all of them so we don't have any problems. Oops. Okay. So if we run this, it's also going to work again, or maybe not. Main. Do I change anything here? I'm just going to delete this example. Can go back to it later. So it all works now again. It's the same bot. Skull, okay, pure script, nice, right? But we haven't seen the effects of those changes yet. The effect is that we can do this, and it saves, it compiles now, and it works. Okay, so we can answer multiple times. We can answer here. We can answer from here, or maybe not. Yes, because we haven't implemented that. Right, because here we need to be in an ask state, but we haven't implemented that same function for ask. So that's left to do. We can do that right now. Right, we have added this ask answer constraint for answer, but not for ask. So we can do that too. And S here. Not all of it works. Yeah, not entirely sure of why it's not working right now. Answer produces an ask state, but yeah, it is ask answer here, so it should be fine. Yeah, this should be working, but I'm not entirely sure of what is happening right now, but it should have been working. So yeah, that's left as an exercise to read. But anyway, like, is any of you able to tell? Thank you. Is any of you able to tell like what exactly is the semantic effect of adding these constraints, right? Of like solving this first exercise, like that, since we're able now to ask or answer in every transition, in every state, what is exactly the semantic effect in the protocol, right? What is like the business effect in the protocol now?
There's two more arrows.
Yeah, sort of, but like what guarantees have we lost, and what are the guarantees that we have left now? Before we had the guarantee that it followed this protocol, right? That after answering something we can only ask and we stay in that loop. So we have lost that now. So what is the single guarantee we have now? Single two guarantees, actually, that we have now.
Because we can get to answer only from start and finalize only from ask.
Exactly. Is that we are guaranteed that our chatbot is going to interact at least one time with a user. We already had that guarantee before, but we now only have that guarantee that the chatbot is obliged to at least answer once. And that's the only thing that we can assert about this when we have this new protocol, right? That we have these two loops here and there. Okay? So hopefully that demonstrates the effect of like altering these protocols, and that's the effect it produces in business rules. So yeah, anybody has any questions about anything? Any ideas, anything you might want to try? I think we have some time, yeah, 10 minutes. No? Okay. So there are some more exercises here, like how could we make the DSL strictly applicative? Because now we're able to, for example, depend on previous results, right? Like the language in order to produce other ones. I don't think it makes more sense now to do that, like, but we can think of how could we do that and what are the effects of doing that? What are the implications? This tip is false because I've changed a few things. I'm going to remove it. And some other food for thought, like can you think of a simpler way to express the same DSL with the same protocol? And how would you improve the domain modeling? Because this is like, we're talking about software engineering here, and it's often the case that we as developers must speak up and tell that something is wrong, that something could be done better, right? How exactly would you improve the domain modeling, and how exactly would that affect your DSL? Okay. Yeah, I think I'll have to wrap up now, and I can show some cooler examples later. So wrapping up, we have seen that language is the, oh, my highlights appear now, yeah. So we have seen that the language is the essence of abstraction, right? That whenever we're describing something, we're domain modeling, whenever a product manager tells us something, we always frame these things with language. We always describe these things, specify these things with language. And a language can be seen as a pair, syntax plus semantics, and we can write tiny languages embedded in Haskell or PureScript too that correctly model a domain and help us solve problems in those domains. And we can make use of some fundamental type classes, such as monoid, applicative, and monad, and their indexed versions as well, in order to model a language more ergonomically and safely. And we can define the syntax of a DSL in Haskell in terms of its abstract syntax or its semantic domain. And that's like the duality of deep and shallow embedding. And we can also use type classes and instances to embed extendable DSLs in Haskell, such that we have the vertical and horizontal extensibility properties. And that's tagless final style. We can leverage Haskell's powerful type system in order to make our DSLs more expressive and safe with indexed types, like essentially not just indexed monads and indexed effects, but indexed types in general. And in order to do these things, creativity is key, but respecting the laws is important. And more important, I'd say, is like getting used to it, practicing it, so that you gain intuition for these things. And this is just like personal opinion, and also some stuff that I've read in a few papers. The good about DSLs, about using them, is that you get a good tool that can model all of this stuff, and that's at the same time practical and ergonomical to use. And it gives us separation of concerns if we use some techniques in order to model our DSLs better. We give our developers high productivity, because some of you might have experienced that from the form builders thing, that we can quickly define some new forms, some rather complex UIs using just a simple description language. We have some highly maintainable design if you use the correct techniques, of course, because DSLs often simplify code, so we have less lines of code, and that leads to more maintainable code. We have some highly portable design, because we can make the separation between syntax and semantics, and we can also always implement new semantics and new interpreters to port these things to some other environments. And we have some opportunities for reuse, given the separation of syntax and semantics. We have user-enhanceable systems, because we can, for example, open source these things, these DSLs, so that users can build their own better stuff on top of that. We have fewer bugs because of types, right? We have improved adaptability too, because, again, of the separation between syntax and semantics. The bad thing, though, is that, as with any abstraction tool, it's always a hard design problem to cook up all of this stuff. You have some sort of upfront costs because you need to build a DSL, right? They just don't fall from the sky. And in some cases, we have a tendency of using multiple languages, and that can lead to some sort of language cacophony, where you, especially in the language-oriented programming setting, you have multiple languages, all of them communicate with each other, and you have to know all of them, right? Types surely help in this case, but it can get confusing depending on what exactly you do. And maintenance can sometimes be painful. depending on the techniques you use, okay? If you like to extend the DSL, for example. And the ugly, yeah, there's nothing ugly about DSLs. And for further reading, I recommend, if you have some interest in looking for monad transformers, free applicatives, free monads, these type classes are very useful too. If you can derive some instances for those for your language, type level programming, also some function combinators, they can be very handy in order to in order to develop a DSL and prototype a DSL quickly, and abstract interpretation. There shouldn't be an S there. Abstract interpretation.
Right?
Sorry? Co-ionator, yeah, that's a typo too, thanks. I'm going to fix all of those before posting them in the channel. And yeah, I would invite you also to share your thoughts and conclusions on what you liked about it or not. And that's pretty much it. If anyone has any questions, anything they'd like to say, they'd like to share, anything at all. Yep.
So I'm kind of curious about the idea of index types. Is it essentially allowing you to encode sort of the stateful information on the type level to
Yeah.
prevent you from just add additional constraints
Let me see if I...
based on like just a phantom type in general?
Yes, I'm not sure if I can find the exact slide here, but yeah, I won't be able to find that. But anyway, like the difference between like a normal parameter to a type and an index is that an index is a parameter that depends on the value, you know. And with JDTs, we can see that where, for example, let me go back to this thing here, okay. Oh, this is not an example of an index, unfortunately, but...
So like the applicative IX monad.
Exactly.
Additional parameters.
And yeah, the thing is that they change from the result, you know.
And those are essentially just encoding information on the type level?
Exactly. And that's essentially like lifting types from the values. You know, you're gathering some information here from the value. It's sort of like this crude version of the dependent types. I'd say I'm not entirely, if anyone here is a type theorist and can correct me, please. But I believe that it's some sort of way of mechanism of like extracting information from the values and lifting this information to the types, you know, so that you can get, for example, an expression. I don't know, if you develop a tiny language that has support for both Boolean and integer expressions, right? You can write a syntax tree with a GADT such that expressions that manipulate, that produce an integer, you track that information in the type argument, you know, and you use that as an index, right? Such that the expressions that produce integers track that information at the type level. That's what indexes can be used for. Yeah.
Thanks.
You sure? So, any questions, curiosities, thoughts, conclusions, anything? Okay, so that was pretty much it. Thank you all for attending.